Right. Yeah, my name is Patrik Flammer. I'm an editor for Genome Medicine and BMC Medical Genomics, and I'm here with Terence Strick from the École
Normale
Supérieure.
Very good.
In Paris. And yeah, we're going to talk about some of your research on single molecule DNA interactions. Yeah, we had a brief conversation before about how you bind the DNA to like rigid surfaces for to study protein interactions and protein DNA interactions. So do you want to sort of say a few words about that?
Yeah, it's a very simple idea, and you start out by mixing the molecule that you want to apply force to a first physical support. So in this case, it's a small magnetic bead. And these are the same magnetic beads that have been used for 20, 30 years now. They were developed originally by Dyno in the Netherlands. And it turns out to be the same basic technology and chemistry that allows to make monodisperse beads for protein chromatography. So the resins in the chromatography columns were actually the first applications for these beads. And then they decided they could put some magnetic material in them, which would allow you then to separate molecules by putting a magnet to the side of your tube and pull on the molecule. And so I realized that you could then, if you attached your molecule of interest at another end to a glass substrate, then you could actually start to pull on the molecule and apply force. And so we did this with DNA by attaching DNA molecules, which are long strands, at one end to a magnetic bead and at the other end to a glass surface, and then put it on a microscope and apply a pair of magnets above it and use the magnet to generate force and torsion on DNA. And manipulate the mechanical properties of DNA and then look at how it reacts. To some extent, a bit like a twisted garden hose, you know, or twisted phone cord, but now there are no more phone cords. So the analogy doesn't work anymore.
Yeah, well, so you can then sort of see the protein interacting with the DNA, and you mentioned something about DNA breaks and break interactions. So is that more the sort of physical interactions of the pathways, or what was the aim there?
So yeah, I mean, the mechanical properties of DNA, as you can imagine, are greatly modified if it's broken. If you have a single strand nick, then it won't accumulate supercoiling anymore. You can rotate the bead as much as you want, but there's not going to be formation of any torsion in the DNA. And so you can do an experiment where you're continuously winding the bead and continuously winding the DNA, and if the DNA has gotten a single strand break, then the bead will not move to the surface under continuous winding. But then if you have DNA repair system in there, such as the one that is involved in single strand break repair, then it'll repair the nick, and the DNA will start to accumulate supercoils, and the bead will move down to the surface. And so you can measure in real time the moment between incision, because we have an enzyme in there that regenerates a nick, and the moment at which the DNA has been repaired. So actually, this is something that we've started to do on to study single strand break repair, which is one of the big successes in cancer therapy recently in olaparib and PARP inhibition, which is a mechanism to try to prevent metastatic cancer growth in BRCA patients, actually. So yeah, the idea is that the mechanical properties of DNA are a very fine sensor for what's going on on the underlying molecule. And we exploit that, and the mechanical properties of DNA are now really well known. And so you can really use those mechanical properties as a real-time detector for what proteins are doing on it.
And you can sort of detect the time it takes between the nick and the repair.
So it's a real-time assay at single molecule resolution. And so one of the advantages of that is that we can work at remarkably low protein concentrations. So because the detection ability is so sensitive, you don't need to build up a signal, you don't need to amplify your signal, it's right there. And so oftentimes we have conversations with colleagues and competitors where we're trying to explain we're able to do these experiments at picomolar concentrations. not micromolar, millionfold lower, thousandfold lower.
Yeah.
Where we think that we get rid of a lot of side reactions and artifacts, and yes, but the point is also, as you mentioned, that we do want to get the real pathways. We do want to rebuild the actual on pathway steps.
Yeah.
And so that you do, using mutants, using controls.
I imagine with the lower concentration of protein, you've got much less protein-protein interactions, which could lead to spurious results. And
a lot of these proteins, have multiple DNA binding sites.
Yeah.
So it's kind of like a monkey swinging from the branches.
Yeah.
A protein grabs here, it grabs here. The DNA slowly condenses.
Yeah.
And actually, that's been a bit of a problem because. In a number of projects, including this one on single-strand break repair, the first few months were about finding that right corner of conditions, the right salt concentrations, the right protein concentrations, where the DNA wasn't just systematically getting glommed together.
Yeah.
And that worries us because we can see this, and so we worry about it, and we know that we have to eliminate it if we want to measure something. But we also know if we're seeing it, it's happening in everybody's test tube.
Yeah.
It's just that they can't see it because they're not actually looking at the global conformation.
Yeah, they can't see that in a. Yeah.
And so as we heard, this Yogi Berra quote yesterday. You can see a lot by observing. It's true. Sometimes you see things you would have rather it not be the case. It would have made your life a lot easier, but it's there and it's going to prevent your measurement from happening.
Yeah.
And you know that the DNA is not getting glommed together in vivo.
Yeah.
It stays fluid. It's not getting coated.
Yeah.
So there are advantages and disadvantages to seeing all these things.
Yeah.
The first is that you have to get rid of them.
Yeah. Yes. So just when you say the DNA is not clumping together in nature, you also mentioned something about using the DNA itself as a polymer substrate for protein interactions.
Right.
So I thought that was actually quite fascinating to actually use DNA as a substrate for non-DNA interacting proteins.
Yeah, DNA is just a remarkable molecule that has no equivalent in anything else. It's very stiff, and that means that you can actually use it as a scaffold.
Yeah.
Which is what we were talking about, and so. We use the DNA now as a kind of string onto which we can assemble proteins using kind of advanced chemistry methods like so-called click chemistry and all the tags that have been developed that allow you to attach proteins to other things. And so we can decorate the DNA now with drug molecules, with proteins of interest. So imagine you have a piece of DNA that's of length 1. And at 1/3 along the way, we put a drug molecule, say rapamycin. And then at 2/3 of the length along the DNA, we put the target of rapamycin, which is FKBP12. And then we can watch if the two bind, then it sequesters the third of the molecule that was in between them. And so your molecule is 2/3 the extension. Right. And when it falls off, you return to your full extension. And you can just actuate the DNA and just watch the length change as the molecules bind and unbind and bind and unbind, and so you get the kinetics just by watching it. And you were saying your background is in chemistry and biochemistry. We really want to use this to probe chemical entities. Drugs on proteins, and then eventually, two chemical entities binding to each other, and maybe, as we were saying, graphene sheets. And so this is really because the mechanical properties of DNA are so robust. It's such a gorgeous molecule.
So you could use that for drug discovery as well, and I know there's a lot of drug repurposing as well.
Yes, so actually that's something that we have a project that's funded by the French INSERM, the French equivalent of the NIH, where the proposal is to see if we can use these single molecule approaches to do drug screening. So the great thing is that we haven't promised results one way or the other. We're going to do it blind. People are going to give us molecules that they've already characterized, and we'll see if we can recover something, and then we'll do a rescreening of a publicly available library, a library of pre-approved FDA compounds, and we're going to see if we can recover in batch screening the compounds that have given hits. And so the problem with the single molecule approach is that the throughput is not super high, But the idea is that you can make you can mix pools of drugs.
Yeah.
And mix 500 drugs together, and then if you see a hit, then separate into 2 batches of 250, and test each batch and figure out which batch contains the activity, and then divide that one again until you find your compound. And the great thing about that is you double the number of molecules you can screen with just one more experiment.
Yeah.
So it's like using the exponential.
It's the book sorting
Exactly.
problem.
Yeah.
Yeah, that's actually really fascinating, because the advantage of repurposing drugs is quite obvious. It's a drug. It's there. It's been tested. We know it's safe. But what does it actually do? And I think there's quite a lot of need for that.
Right.
I think, and interacting with proteins, that's definitely sort of important thing forward. What else do you think you can use actually these DNA sheets, these DNA polymers as a substrate for? Is there anything else you could?
There's a whole field which we're not yet really involved in. We kind of look admiringly from afar. It's called DNA origami.
Right. Okay.
Where they can fold the DNA into shapes, just like a Japanese origami. And it started out, with making a smiley face, making very simple 2-dimensional shapes. And in the last 5-10 years, it's just exploded, and people can make 3-dimensional structures out of single-strand DNA, in which the structure is guaranteed by the fact that you're using oligonucleotides to staple the strands next to each other and hold them together. Yeah. So they were able to make the bundles of these artificial DNA molecules and literally build structures out of them. So one of the ideas, there's a beautiful paper where they use this as an artificial pore. Yeah. That can stick into a cell and allow transport through this kind of chimney. It's a chimney built of DNA with a big channel in the middle. The idea of using these as drug payloads. Yeah. You could encapsulate the drug in a kind of sphere of DNA, and then by adding an oligonucleotide sequence that would kind of peel off the staple.
Okay.
That's helping to hold the sphere together. You would then open the sphere and allow it to release the drug into solution. Right. So we would like to do some of this, but time is short, and unfortunately, science today isn't as it's hard to do exploratory science today. You usually have to have a grant, and then you use a bit of the money to do these small things on the side, because the number of exploratory grants has gone down. Yeah, it's quite sad that it actually happened, and you can't get a grant without having having data, and you can't get data without having it's a never-ending problem. No, so I call this submarine projects. You're below the surface. Yeah. Nobody needs to know. Nobody needs to know. The amount of money that's being used is negligible, because the whole point is that you're not going to waste your time on top of it. Oh yeah, of course. On a small kind of. There's just sort of the ideas that come up, and that sort of open potentially new avenues into new research and. So the scaffold idea I was telling you about came from a conference I went to on DNA repair a few years ago, and I think I spent 3 to 4 years fiddling around with it and trying out different ideas before finding one that actually worked. And when we were finally able to build this first scaffold, it worked the first time out of the box. No, that usually doesn't happen. It was literally the first time we put it under the microscope, we started to get what we wanted out of it. But it was building the molecule in the first place that was the challenge. And then once it was there, it did what it was supposed to do. Yeah, there's so many opportunities coming up out of that. That's and and in the context of these vaccines, these mRNA vaccines. I mean, it's an era of biologics. Disease is going to be cured, by biological molecules, side by side with the chemistry. Yeah. So it's a really exciting time to be in the drug development space. Although I gather it's extremely costly. Well, it's until you actually hit the jackpot, and then right. But I don't know how many molecules they have to try. There's something called I heard about this. There's Moore's law, which tells you about how many more transistors you can pack into a certain space, and how quickly that number grows with time. I think it doubles every 18 months. And apparently, in the drug development and discovery space, they flipped it around. It's called Eroom's law, which is Moore's law backwards.
Yeah.
And this one says that the number of successful compounds that you're able to come up with per $1 million per year is itself an exponentially decreasing function.
Yeah.
So like if 30, 40 years ago for $100 million, you could come up with 20 or 30 compounds, and now for the same sum, you're happy if you come up with 1 or 2.
Yeah. It's the sort of having a strong basis in research of like what has been researched before is not always the. There's less to discover.
Yeah,
well, there's still plenty to discover, but
there's plenty to discover, and this development of the AlphaFold and structural prediction.
Yeah.
I mean, it's really the rate of discovery is just breathtaking.
Yeah.
And I guess one of the challenges is going to be how not to be so specialized. You're specialized in a pathway.
Yeah.
Or in one kind of molecular interaction, and you focus on that exclusively to too many other things, because the rate of discovery is so high.
Yeah.
It's hard to keep up.
Yeah, absolutely.
So you must see this as an editor too, right? I mean, you guys are just swamped with novelty all the time, and
it's sometimes really hard to sort of disentangle what is actually. For us, it's really difficult to see sometimes what is it's going to be the real breakthrough, what is not going anywhere, because I mean nobody knows.
Yeah.
And, it's.
So it's a form of discovery, and you have to wait 5-10 years to see was this the great paper that that's cited.
It's I think in that sense we're really in the same boat as the researchers, because we have where we can guess, we can sort of look at what other people have done. We can do what is actually where is interest in the field, but ultimately nobody knows. We don't know. We try to give novelty a chance whenever we can, and hoping that creating all these opportunities will actually lead to some more interesting discoveries. Yeah.
No, it's I've been very fortunate to work with some of your colleagues at Springer and Nature, and they're a really great group of people, and one of them, one of your colleagues turned us down for a paper, and we were a bit bummed, and we said, but we think they can do this and that. We think that there's some really great improvements with it, and there's this additional thing we could do, and she explained it really well to us. She said, look, if you're on the verge of a big improvement on this, we don't want to publish this version, because in a year, if you come out with that big improvement, then the one we'll have just published will never get traction, and it's the other one that's going to get traction. So you have to think about it from both sides, and it I learned that day that the editors are actually your best advocate.
Yeah, this is what we're trying to get people to be interested in what we publish, and we try. For us, it's really hard actually to turn down authors to say like, look, we can't take that one, but it's always good to have the interaction, saying like, look, if we can work together and we can make it into something that will be interesting to the wider audience as well. This is the bit that I actually really like about it.
And I think that is still a super important added value in the formal journals as opposed to just open access. Because there's so many papers where it's going to take time to filter out whether they were the right ones. And as a reader, it's kind of hard to know, is this one, do I have to spend time understanding this one really, or should I be spending time on that one? And to some extent, it's easy to say, follow the authors or follow the labs. I mean, there's too many parameters, and so at some level, if there's if the filters if there are even fewer filters, sometimes I find that a bit worrisome. So obviously things like the bioRxiv, which was founded here, right? I mean, this is the heart of bioRxiv. It's great to be able to get early access to things. But I don't find I'm not sure the commentary mechanisms haven't really caught on, I have the impression. People don't really want to pile on publicly like that.
No, I think this is a hesitancy of like sticking your neck out. I think that's the thing, and it's also difficult because they're not reviewed. They're not like they could still have errors in it. So yeah, it's
part of the process.
Yeah. Okay. Thank you for having a very interesting discussion about your fascinating research, and
great pleasure. Thank you for your time as well.
Thank you.
Thank you very much.